Pleasant day, everyone. I am Rich Nuevo from Cebu Technological University. Allow me to present to you our output of our research entitled the CTU AgriFresh Urban Salad Factory. If I may. Okay, so what we are currently in right now. So we're basically already in the new normal. So what's wrong with the new normal? So at least this time it already sort of like uh, tapered down to more or less the old normal. But still, the movement of both goods and persons is disrupted. So from time to time, there are delayed trips. On top of that, there's the soaring fuel costs. So, and at the same time, um, goods and goods, particularly the fresh foods from farm, arrive late and less fresh, and at the same time more expensive. Um, Problem is our consumption patterns are basically the same even before the pandemic and up to until now. Um, the obvious solution to this is to produce food where it is consumed. So to partly address this problem, we developed a small footprint hydroponics setup. So what is hydroponics? So hydroponics is basically the growing of crops in soil-less conditions. That's why it's called hydroponics, because it's basically grown in water. So as you can see here in the figure, uh, there's here the plant bed. So the crops are there with a growing media. It's not soil. Normally, in our case, we used coco peat. Others use foam or perlite or stuff like that, or any ceramic material that is basically used for anchorage. And then the roots are submerged in water. This water is actually nutrient laden, and it is recirculated again and again. So it basically goes around the system through a pump that's powered by typical electricity. So in our case, we used an aquarium pump. So water is pumped from the sump. So this is, again, as mentioned earlier, nutrient laden. It's pumped up into the grow beds, and then it will drain back into the sump and then goes back into the grow beds. So it's just like that. So the optimum conditions are maintained because of the nutrients that's available in the water. So what do we intend to do? So the objective basically of our study is to develop a micro hydroponic setup small enough that it can be used at home. So as much as possible, we try to meet the following criteria. One, it uses locally available materials. Second, it should have a small footprint because it's going to be used at home, or the extra spaces that we have at home. It, as much as possible, it will employ automation, and then at the same time it monitors water quality, and finally to have a timing system for intermittent flood and rain cycles. Okay, so what we did was basically initially we did some brainstorming, taking consideration all those criteria that I just mentioned earlier, and then after the design process, we went into the procurement of materials, and then finally for fabrication and testing. So that's what we basically did. So come up with a design and then fabricate the design in-house. So this is our initial result. So this is actually our first iteration. It's an A-frame. It has 1, 2, 3, 4, 5, 6 layers. Each plant pipe is accommodating 6 plants at the same time. So that's 6 by 6. All in all, it's 36. Multiple levels. The next picture here shows you the setup done at night. So we did some extra lighting, so based on the principle that it can be grown indoors. So this is actually set up outside. So this, as mentioned, this is our first iteration. And then there's grow lights. So the grow lights, if you've noticed, is something like pinkish. It's because we just used the wavelengths that are actually needed by plants. It's the wavelengths near the blue and the red frequencies, no, and then the greens are not basically used, so it's just a waste of energy, so we use that. So initial results have shown that this I think we had like 3 rounds of harvest on this setup. It was okay, but I feel that it's just too much for a single home. So our oh wait This one are actually the materials. The total cost is about 7,000 pesos for this setup. No, so a typical angular bar are here. The PVC downspout is the rectangular one where we planted our crops. We have a submersible pump. I'll be showing some pictures later in the next slide. PVC pipes, various fittings, the storage box as the water sump, and then the microtube fittings for the microtube and other stuff. Labor was estimated at around 200. This is basically it. So this is the downspout tubing. This is manufactured by Atlanta. They call it Atlanta Duracon downspout. So its dimensions are 2.5 from this to this, 2.5 inches. From here down is 4 inches, and the length of the pipe is 8 feet. So in our setup, we cut it into two. Since the holes are 8 inches apart, one hole pipe can accommodate a total of 12 holes or 12 planting holes. In our case, we use half of it, so we just have 6 planting holes. This is the actual aquarium pump that we used. It's 24 watts and is claimed by the manufacturer to pump water at a rate of 4,000 liters per hour and up to a height of 3 meters. This one is actually the rubber grommet. We are not very familiar with this, but this is the fitting that we use to fit this pipe onto the downspout. This is the downspout, so we can see inside based on the hole, this one. So it drains here. So the drain system is actually fitted by that. So we are not using any other material. This way we could readily adjust the height of the PVC pipe that's inside. This is the microtubing, and this is the connector, the barbed connector. So we basically drilled holes onto the 1/2 inch PVC pipe. This is connected directly to the aquarium pump. So it's the one that takes the water up and then distributes into the different planting channels. So it goes out with that. It's connected using this connector, and this tubing is actually has an inside diameter of 4 millimeters and an outside diameter of 7 millimeters. As mentioned earlier, it cost us about 7,000 for this one, for this setup. After that, we have a second iteration, which is actually smaller. So, as mentioned earlier, the first one has a total of 36. It can accommodate a total of 36 plants. This one, it is actually just 6x4, a little bit smaller. It's just a table type, and the system is there, so it's very clear. And it now employs a little optimization, a little bit of automation. I mean, using the water quality monitoring system. So 24 holes, smaller, and it's equipped with an Arduino-based water quality monitoring system. We're basically monitoring the total dissolved solids, or TDS, which is a proxy of the measure of the amount of nutrients that's in the water, the pH, which is also very important for the crops, and then the temperature. So it's these 3 parameters are being measured every 12 hours and is displayed on a small LCD, this one here. I have an actual picture in the succeeding slides, I think. So here are basically the dimensions. It's 32 inches high, 28 inches wide, and 48 inches long. And then, yeah, and then the box here for that houses the electronics. Okay, so the electronics is basically driven by, as mentioned also earlier, by an Arduino. It's actually housed in a 3D printed box. This is the actual one. And then you can find here, we have here a module for the TDS meter. So the TDS is actually just computed from conductivity. So we have 2 points of contact with a known distance, and then the conductivity of the water is measured by the TDS meter, and applying a certain constant, we came up with the total dissolved solids. Here's another sensor that's also connected to the system. It's basically a single wire temperature system, and another one, finally, the pH module with the pH sensor. So I don't know if you've noticed this one, its initial results, because this research is still ongoing. So this is what we've done so far. We hope to complete this one by the end of this year. Okay, so we have, for future direction, we cannot draw exact conclusions yet at the moment. As mentioned, this is an ongoing research. We have here, of course, right now we are still calibrating the electronics so that we can get accurate readings. There are some times that we get some fluctuations in the readings, and then we intend to come up with another iteration that can be used totally indoors without sunlight using artificial grow lights. We also intend to improve the second iteration, the smaller one, by adding a UV plastic to protect it from rain, considering that it's already being irrigated with water continuously with the nutrients, so it does not need rainfall anymore. We just need the sunlight for that. And then a protective net shall as well be included on that. And then finally, for the electronics, we intend to increase the size of the display. Perhaps we'll be using a touch panel display, so it will be touch screen now, so we can operate this one for monitoring and include an alarm system if in case the values will be out of range in cases of that. So possible be doing that. Yeah, that's basically it. Thank you very much for your time. If you intend to collaborate in the future, here you can find there my contact information. Again, thank you very much. A pleasant day to all.